Hello, in this session we will try to understand free energy of mixing of gaseous reactants and products and spontaneity. By this process, we will also understand why gaseous reaction never go to completion. Means, suppose there is gaseous reactant and products in equilibrium, then the equilibrium will never go towards 100% completion. Means all the reactants will not go and give 100% product. So we'll study why that happens, why gaseous reaction never go to completion. So we'll start with a general reaction where gas A is being converted to gas B. Suppose it can be isomerization reaction or any reaction, any simple reaction where gas A is being converted to gas B. The Gibbs energy of reaction mixture at any extent of reaction is given as G is equal to Na mu A, Nb mu B. Actually, Gibbs energy is given as VdP minus SdT plus mu A dNA, mu B dNb and all those things. But here we are assuming that temperature and pressure are constant. So the other terms will vanish out and we will be left with only Na mu A and Nb mu B. The actual dependence of Gibbs energy on temperature, pressure and number of moles of species present in a system we have discussed already. So in previous lectures we have discussed that. So I'll not go to the details. I'll just say that at constant temperature and pressure, the Gibbs energy is given as Na mu A plus Nb mu B. What is mu A and mu B? It is the chemical potential of component A and B. What is Na and Nb? This is the number of moles of A and B respectively at any point of reaction. I am saying at any point of reaction. So suppose suppose we will study at equilibrium. Then suppose the reaction is started with 1 mole of A, the simplest case 1 mole of A and 0 mole of B. So at equilibrium amount, let the reactant amount is 1 minus xi and product amount is xi. Xi is the extent of reaction. So what is the mole fraction now? Number of moles of A is 1 minus xi and number of moles of B is 1 xi. So we'll deal with number of moles only. We'll discuss mole fraction. So what will be the mole fraction now? The mole fraction will be 1. The total number of moles will be 1 because number of moles of reactant is 1 minus xi and number of moles of product is xi. So now total number of moles will be 1. 1 minus xi plus xi is equal to 1. So what will be the mole fraction of reactants? 1 minus xi by 1. Mole fraction of product will be also xi. So the number of moles and mole fraction is same. So here number of moles of A is 1 minus xi at equilibrium mu A, and in place of Nb I am writing xi mu B. So this is Gibbs free energy expression for the A to B conversion at equilibrium. Now we know that chemical potential is given as mu A is equal to mu A0 or mu A at standard state plus RTLN PA by PA0. PA is the partial pressure of component A and P0 is the reference state pressure. Generally it is the standard state pressure, which is 1 atmosphere or 1 bar. So partial pressure of component A can be written as mole fraction of component A into total pressure. So if I substitute partial pressure as mole fraction into total pressure, I'll get RTLN XA plus RTLN P by P0. This P is total pressure, XA is mole fraction of component A. Now what is mole fraction of component A? It is 1 minus xi because the total number of moles is 1. So mole fraction is number of moles by total number of moles. So I will get mu A0 plus RTLN 1 minus xi plus RTLN P by P0. This is chemical potential for component A. Similarly, chemical potential for component B will be mu B0 plus RTLN xi. Xi will be the mole fraction of component B plus RTLN P by P0. Again, P is the total pressure. Now, if I substitute these two mole chemical potential expression in the Gibbs energy expression, what I'll get? What was the Gibbs energy expression? 1 minus xi mu A xi mu B. If I'll substitute mu A and mu B, what I'll get? 1 minus xi. This is expression for mu A. Xi, this is expression for mu b. So if I'll open up all the expression, I'll get a lengthy expression like this. So I'll try to arrange mu a terms, mu a 0 terms. So I'll get 2 mu a 0 terms. I'm getting 2 mu a 0 terms. So I'll arrange the mu b 0 terms also. There is only one mu b 0 terms. Then RT ln p by p0, RT 1 minus xi ln 1 minus xi plus xi ln xi. If we can arrange, it is simple. It can be obtained with a simple rearrangement. There is not much of difficulty here. Now further rearrangement gives what? G is equal to mu a0 minus mu a0 by minus mu b0 into xi plus RT ln p by p0 plus delta mix G. This is Gibbs energy of mixing. What is delta mix G? RT, this whole term, RT 1 minus xi ln 1 minus xi plus xi ln xi. So this is the Gibbs energy of mixing. How this is the Gibbs energy of mixing, we'll see, just shortly we'll see that. And the other first three terms are obtained from these terms. Okay, so there are totally 4 terms. One is mu a0 minus the first term. The second term is mu a0 minus mu b0 into xi. The third term is RT ln p by p0 plus there is Gibbs energy of mixing. How this Gibbs energy of mixing is obtained, I'll just illustrate. So this Gibbs energy of mixing is obtained due to mixing of 1 minus xi moles of gaseous reactant A with xi moles of gaseous product B. So again, there is this reaction is A is going to B. We'll started with 1 mole, 0 mole. Then at equilibrium amount we are left with 1 minus xi mole and xi mole. In the previous lectures, previous few lectures, we have discussed that the Gibbs energy change due to mixing of gases is given as nRT xa ln xa plus xb ln xb. What are xa and what is xa and what is xb? These are mole fraction of component A and component B respectively. So again, this expression we have already discussed in our previous session, so I will not discuss this. So this says simply that this is the expression for Gibbs energy of mixing. Now what is xa here? Xa is 1 minus xi because total number of moles is 1. And mole fraction is number of moles by total number of moles. So mole fraction of component A is 1 minus xi. Mole fraction of component B is only xi. So if we substitute that, we'll get delta G mix, or the Gibbs energy of mixing is RT 1 minus xi ln 1 minus xi plus xi ln xi. So this is the this term appears only here. So the total terms are replaced by delta G mix or Gibbs energy of mixing. So my equation 62 is important. The equation 62 contains 4 terms and it gives an expression for Gibbs energy and it contains 4 terms. The first term is mu a0, the second term is mu a0 minus mu b0 into xi. The third term is RT ln p by p0. What is P? The total pressure. And delta Gibbs energy of mixing term. So my total Gibbs energy consists of 4 parameters. Okay, so we'll try to understand this equation 62 in a better way. So let's understand equation 62 in more detail. So this was the equation 62. So there are 2 prominent contributions taking place. As I said, there are 4 terms. So out of the 4 terms, 2 prominent contributions are coming. The first 3 terms are linear terms. Again, I am repeating, the first 3 terms are linear terms. Okay, and the fourth term. Okay, fourth term is the mixing term. Okay, the free energy of mixing term, the fourth term is a mixing term. So we'll first understand the first 3 terms. The first 3 terms give linear response if the mixing of reactants and product is ignored. If we ignore the mixing of reactant is forming product, so eventually they will mix with each other and there will be a mixing term. But for a moment, if we ignore that there is no mixing, then Gibbs energy changes linearly from its initial value. Okay, this first, if we ignore this fourth term, then that Gibbs energy, G is Gibbs energy. Gibbs energy says it changes linearly from its initial value to final value, as depicted in figure 7b. We'll go to figure 7b just now, and slope of the line is given as delta r g0. Okay, so the first three terms are linear terms. It says if there is no mixing term, then the Gibbs energy will simply decrease linearly from pure reactant to pure product. Now what happens, the second contribution? The second contribution comes from the mixing term. The mixing term that causes the minimum in a plot. Suppose we plot G, the Gibbs energy and extent of reaction, then this mixing will cause a minimum in the plot. Okay, from say figure, again we'll go to, just now we'll go to figure 7.7b. It is seen that initial extent of product formation is less. So now we'll go to figure B7b, then we'll understand. So this is figure 7b. So this is taken from Atkins' book. So this is a plot of Gibbs energy and extent of reaction. Suppose this is pure reactant, y-axis this side, left hand side, and y-axis at the right hand side is product. So if there is no mixing, only the first three terms are there, then Gibbs energy will decrease linearly. This blue graph is for without mixing. The first three terms will contribute for a linear decrease of Gibbs energy with extent of reaction. Now what happens when this linear decrease is due to only the first three terms. Now suppose the first three terms are not there, only the fourth term is there, means only the mixing term is there. The mixing term will give a graph like this, Gibbs energy and extent of reaction. Okay, the mixing term will give a graph like this, means at 50% of extent of reaction will get minimum Gibbs energy. The first three terms are not there, only mixing is there. Okay, but in our actual figure, in our actual expression, there are both terms. The linearly decreasing terms are there and mixing term is also there. So we'll get a graph, graph which is addition of both these graphs. One is linearly decreasing graph and the other is symmetrically decreasing kind of graph. So what we'll get a resultant graph like this. Okay, so this graph is important. At the initial state of the reaction, when the extent of reaction is less, the mixing term is not very heavy. The contribution due to mixing term is less. But towards the end of reaction, when extent of reaction is more, then the mixing term is more. Okay, so it becomes much more heavier on the linear curve. So we'll get a resultant curve like this. The linearly decreasing curve is due to the linearly decreasing line is due to the first three terms, and this parabolic decreasing line is due to the mixing term, and the resultant curve is somewhat kind of elliptical kind of line, we can say. So this curve is important. If we observe this curve, what happens? Every species tries to attain a minimum Gibbs energy. So the resultant curve has a minimum Gibbs energy somewhere towards the product side, but not completely at the product. Okay, the reaction Gibbs energy has a minimum towards the product side. This is the minimum. Okay, but not actually at the product. Similarly, if we look at one more graph, this graph is again for Gibbs energy and extent of reaction. The minimum of Gibbs energy is attained. Suppose here it is 0.7578 kind of. When the extent of reaction is at 0.78, then we have obtained the minimum in Gibbs energy. So that is the state of equilibrium. Okay, it is the state of equilibrium is not towards the product side, means the reaction is most stable when both when both reactant and product are present. It is not that 100% of reactant is converted to product. So this that is the reason why we say that all of the reactant cannot be converted into product completely, because they arrange themselves in such a way that at a particular composition of both reactant and product, that Gibbs energy becomes minimum. So that's why generally gaseous reaction don't goes towards completion. So further we'll try to understand that. It is seen that initially the extent of product formation is less, and hence the mixing contribution is relatively less during the initial phase of reaction. But as the reaction proceeds further, the mixing contribution gets heavier. The sum of two contributions, that is the linearly decreasing contribution and mixing contribution, has a minimum corresponding to equilibrium composition of the system. That minimum is called equilibrium state. Okay. We know that at constant temperature and pressure, the criteria for equilibrium is the Gibbs energy of minimum. So at equilibrium, essentially the Gibbs energy is minimum. That's what it says. Then it says, suppose the chemical potential of this reactant is more and product's chemical potential is less, then only this reaction will go from reactant to product, but it is not 100% transfer. If the mixing term is not there, there is complete transfer. All the reactant will go to product. But if there is a mixing term, then all the reactant will not go to product. Okay, before forming 100% product, they will find a state of equilibrium and they will be happy to be there. They will not go towards complete product formation. So that's why if there is no mixing term, then it will go towards 100% complete product formation. That's what this statement says. Generalizing the above statement, we can say that no chemical reaction of gases goes to completion. Also, it may be difficult to detect reactant at equilibrium if the products have very much lower Gibbs free energy. If the product's Gibbs energy is low, then it is difficult to find out the equilibrium position. That's what it says. So at equilibrium, the system can achieve lower Gibbs energy having some reactants present in the equilibrium state. So at equilibrium state, both reactants are present and products is also present. When there is a mixing term, when there is a gas mixing taking place, there is no way that the reaction will go towards 100% completion. So these two graphs are for Gibbs energy of reaction and extent of reaction. If we take the first derivative will be dg by dxi. First derivative of Gibbs energy with respect to extent of reaction, that is dg by dxi, will get a curve where at the equilibrium state, the curve will have zero value, means the first derivative will have zero value. So that helps in identification of equilibrium position, precise identification of equilibrium position. So in order to find the exact identification of equilibrium position, we can always take a first derivative graph. What it further says, the first derivative of Gibbs energy tends towards infinite when extent of reaction is 0. When extent of reaction is 0, the first derivative is negative of infinity. Okay, when extent of reaction is 1, the first derivative tends towards positive infinity, and at equilibrium the first derivative gives value 0. Now what about the second derivative? If we take the second derivative plot, if we draw a second derivative plot, so this fourth graph shows the second double derivative of Gibbs energy with respect to extent of reaction. It says that this graph will always be positive. Okay, the second derivative has to be positive for the equilibrium to be stable. For any equilibrium that is stable, the second derivative of Gibbs energy must be positive. So with this we will stop here. Next session we will discuss equilibrium constant and and the Le Chatelier's principle. Thank you.